Hello. Lesson 11 is once again all about factorization. I'm going to begin by talking about special form factorizations. Anne is going to follow with several examples and a general factoring strategy, and Candace is going to conclude today's lesson by working the problems that were included on your factor test in your math telecourse packet. So let's begin with special form factorizations. There are three types of special form factorizations. There are perfect square trinomials, there are difference of squares, and there are sum or differences of cubes. So let's explore all of these special types. And let's begin with perfect square trinomials. We're going to begin our discussion by reminding ourselves about a couple of special products. When we square the binomial a plus b, the result is a squared plus 2ab plus b squared. Similarly, when we square the binomial a minus b, the result is a squared minus 2ab plus b squared. These trinomials on the right side of the equal sign are called perfect square trinomials. A squared is a perfect squared term, and b squared is a perfect squared term, and this trinomial came from squaring the binomial a plus b squared or a minus b squared. So the way we're going to take these products and turn them into special form factorizations is we're going to use the symmetric property of equality, and we're going to put the trinomial on the left side of the equal sign and the factorization on the right side of the equal sign. Let's see some examples of this. Let's factor x squared plus 22x plus 121. When I see this trinomial, the first thing that I identify is the fact that the first term is a perfect square. X squared can't get much more perfect than that. And the last term is also a perfect square. 121 is the square of the number 11. So this might be a perfect square trinomial. If I want to determine whether or not this is a perfect square trinomial, the first thing I need to determine is what would I replace for a and what would I replace for b? Well, if a squared is going to be x squared, I think it's pretty straightforward that a is going to have to be x. Similarly, since the whole reason I'm doing this exploration is because I recognize that 121 is 11 squared, if b squared is going to be 11 squared, I guess b better be 11. So if I make these two substitutions, clearly a squared is going to be x squared and b squared is going to be 121. But my perfect square trinomial has form a squared plus 2ab plus b squared. So I need to make sure that my 2ab is also 22x. So let's check it out. Let's begin by writing down our given trinomial, which was x squared plus 22x plus 121. And then let's go ahead and make our substitutions for a and b in our perfect square trinomial form. That would be x squared plus 2 times x times 11 plus 11 squared. Are these two expressions equal? Well, surely x squared equals x squared. 2 times x times 11 is 22x. That's what I was given. And 11 squared is 121. So these two expressions are indeed equal to one another. Consequently, I can go ahead and write my perfect square trinomial as the square of a binomial. Specifically, this perfect square trinomial is the square of the binomial a, which is x, plus b, which is 11. That quantity squared. I knew that it was a plus b because my OI term in the middle here had a plus sign in front of it. If my OI term had had a minus sign in front of it, I would have used the form a minus b, quantity squared. Now, in my part of the lesson today, I'm going to go ahead and leave the check to you, but I really do encourage you to go ahead and do the check. Go ahead and FOIL out x plus 11 squared and make sure that you do get x squared plus 22x plus 121. The reason I'm leaving the checks out is so that I can work through lots of examples and still leave lots of time for Anne and Candace. All right, let's look at 4x squared minus 36xy to the 5th plus 81y to the 10th. Is this a perfect square trinomial? Well, the first thing we need to decide is, are our first terms and last terms perfect square expressions? So let's consider this in kind of a generic sense. How do we decide if ct to the n is a perfect square? Here, c is my coefficient, and t is just some kind of generic variable. It could be t, x, y, z, could be any variable. Well, there's two things I need to consider. The first thing I need to consider is the coefficient the square of a positive integer? Now, you might be thinking any number that's the square of a positive integer is also a square of a negative integer. And you're right. For example, 16 is the square of 4. It's also the square of negative 4. However, when I apply my perfect square trinomial formula, I need to use the positive number for the trinomial formula to work out. The other thing I have to consider is the exponent on the variable. The exponent on the variable needs to be even if the term is going to be a perfect square. So let's look specifically at our given trinomial. Can we write 4x squared as a perfect square and 81y to the 10th as a perfect square? Well, sure we can, because both 4 and 81 are perfect squares of integers, and the exponents on both x and y are even. So if a squared is 4x squared, I think it's pretty easy to see that a needs to be 2 times x. 2 squared is going to give us 4, and x squared is going to give us x squared. How about if b squared is 81y to the 10th? Well, we know that the positive integer that we square that gives us 81 is 9. So that's pretty straightforward. What does the exponent on y need to be in our b expression? Well, let's think about the way exponents work. If we have y to the m and we square it, our powers to power rule says that we need to multiply the two exponents. So ultimately, the exponent on y is going to be 2 times m. We want our exponent on y to be 10. So I think the only way that's going to happen is if 2 times m equals 10. And if 2 times m equals 10, m has got to be 10 divided by 2. To find our exponent on y in our b expression, we need to take our exponent on y in our b squared expression and divide it by 2. So that means altogether that b is going to turn out to be 9y to the 5th. This time we're trying to fit the model a squared minus 2ab plus b squared. Let's see if we do fit that model. So we begin by writing down our given trinomial. And now let's just write down what we get in our formula. We have a, which is 2x quantity squared, minus 2 times a, which is 2x, times b, which is 9y to the 5th. And then we have plus b, which is 9y to the 5th, quantity squared. Now, are our two expressions equal to one another? Well, distributing the exponent of 2 through the expression 2x, 2 squared is 4, x squared is x squared. So our first terms match up. How about our middle terms? Minus 2 times 2 times 9 is negative 36, and our variable factors are x, y to the 5th, minus 36, x, y to the 5th. 9y to the 5th squared. 9 squared is 81. Y to the 5th squared, when we multiply the exponents, gives us y to the 10th. 81y to the 10th. We do fit our model. So how do we factor this model? Well, this time I need a difference binomial squared so that my o and I terms add up to a negative coefficient. So this is going to be my a, which is 2x, minus my b, which is 9y to the 5th, quantity squared. Again, I really encourage you to check this. Expand our factorization and make sure that we have 4x squared minus 36xy to the 5th plus 81y to the 10th. Okay, let's factor 9x squared plus 15xy squared plus 4y to the 4th. I'm thinking this might be a perfect square trinomial. Is there something that I can square that gives me 9x squared? Sure, 3x. Is there something I can square that gives me 4y to the 4th? Sure, 2y squared. So let's see, using these expressions, if we do have the model a squared plus 2ab plus b squared. So my given trinomial was 9x squared plus 15xy squared plus 4y to the 4th. Does that equal 3x quantity squared plus 2 times 3x times 2y squared plus 2y squared, quantity squared. Well, if I square 3x, I get 3 squared, which is 9x squared, 9x squared. How about my middle term? 2 times 3 is 6, times 2 is 12, and my variable factors are x and y squared. Do I have 12xy squared? No, I have 15xy squared. What does that mean? It means that I don't have a perfect square trinomial. And if I don't have a perfect square trinomial, then my trinomial does not factor into the square of a binomial. I need to ditch this approach and find a different strategy for this problem. So the first thing I need to do is erase this expression right here because it does not equal my given expression. And while I'm erasing, I'm thinking about what's going to be plan B. Well, plan B is going to be that I've learned a lot of other factoring techniques, so I guess I better employ one of my other factoring techniques. Now, one thing I could try is I could try factoring by trial and error. But the coefficients on both my first term and last term are non-prime numbers. And that means there's a whole lot of trials and probably a whole lot of errors before I stumble upon my factorization. So I think instead I'm going to use factoring by grouping. So using factoring by grouping, what I need to do is I need to come up with two numbers that multiply to 36, that's 9 times 4, and add to 15. That's the coefficient on my middle term. Now, the first two numbers that come to my mind that multiply to 36 are 9 and 4. But 9 and 4 do not add to 15. They add to 13. Can I think of a couple of other integers that multiply to 36? Sure. How about 12 and 3? And guess what? 12 plus 3 is 15. Those are the integers I'm looking for. So let's go ahead and take my middle term, and let's rewrite it as 12xy squared plus 3xy squared. Now what I want to do is I want to group the first two terms, look for common factors, and group the last two terms and look for common factors. In my first two terms, both coefficients are evenly divisible by 3, and they both have a factor of x. And when I factor out 3 and x, what do I leave behind? Well, from my first term, I leave behind 3x, and from my second term, I leave behind 4y squared. Let's make sure that's correct. 3x times 3x is 9x squared. 3x times 4y squared is 12xy squared. So let's move on to the final two terms. My final two terms, the coefficients have no common factors other than 1, but both terms have two factors of y. So let's go ahead and factor out y squared. What do I leave behind? I leave behind 3x plus 4y squared. Hot diggity dog. I left behind the same binomial I left behind in my first factorization. Let's make sure I didn't make a boo-boo here. Y squared times 3x is 3xy squared. Y squared times 4y squared is 4y to the fourth. So I'm good to go. Both of these terms have factors of 3x plus 4y squared. And when I factor that common factor out, I leave behind 3x plus y squared. Now the next step in this process is to check. However, in the interest of time, I'm going to leave that to you. But please do expand my supposed factorization and make sure that we do get 9x squared plus 15xy squared plus 4y to the fourth. Holy moly, look at these numbers. Well, I'll tell you one thing. After I get past my panic, the first thing I notice about these numbers is that 3 is not a perfect square, and unless I've forgotten my multiplication tables, 192 is also not a perfect square. So right now, I definitely do not have a perfect square trinomial. However, I am noticing something. I'm noticing that the middle coefficient is negative 48, and I know that 3 evenly divides into negative 48. I wonder, does 3 also evenly divide into 192? Well, the quick check is to add up the digits of 192. 1 plus 9 plus 2 is 12. And you know what? Since 3 evenly divides into 12, it must also evenly divide into 192. So all 3 of my terms have a factor of 3, and the first step in any factorization problem is to factor out your common factors. So let's take 192a to the 12th minus 48a to the 6th plus 3, and let's factor out our common factor of 3. 3 goes into 192 64 times, so I leave behind 64a to the 12th. 3 goes into negative 48 negative 16 times, so I leave behind negative 16a to the 6th. And 3 goes into 3 one time, so I need to make sure I remember to leave behind a term of 1 so that when I distribute 3 through this trinomial, I do indeed get 3 terms. Hey, check it out. 64 is a perfect square. 12, the exponent on a, is even. That's my first term. My last term is 1. 1's also a perfect square. So I might have a perfect square trinomial. If a squared is 64a to the 12th, then the coefficient on a must be 8, and the exponent on my little a in my expression for capital A must be half of 12, which is 6. Capital A is a times little a to the 6th. What does b equal? Well, if b squared is 1, the positive integer that you square that gives you 1 is 1. So b is 1. My model here is a squared minus 2ab plus b squared. When I factor out a common factor at the beginning of my factorization process, I need to make sure that I don't make a common error. And a common error is to forget my common factor when I move to the next line. So let's make sure I remember my factor of 3. Now, if my trinomial is a perfect square trinomial, the model it's going to fit is 8a to the 6th quantity squared minus 2 times 8a to the 6th times 1 plus 1 quantity squared. Does this match the line above? Well, let's check it out. 8a to the 6th squared, 8 squared is 64, a to the 6th squared, using the power to power rule, is a to the 12th. Minus 2 times 8a to the 6th is indeed minus 16a to the 6th, and plus 1 squared, you betcha, is plus 1. So I do have a perfect square trinomial. So let's go ahead and factor. I'm going to factor this into the square of a binomial. Specifically, I'm going to factor it into the square of the binomial 8a to the 6th minus 1. Again, please do make sure that you check that we have the correct factorization. Let's factor x to the 4th plus 15x squared plus 64. If a squared is going to be x to the 4th, a needs to be x squared. If b squared is going to be 64, b needs to be 8. Do I have the model a squared plus 2ab plus b squared? Well, you know what? I can see straight off I don't have that model. 2 times a times b is going to have a coefficient of 16, 2 times 8. I wasn't given a coefficient of 16. I was given a coefficient of 15 on my middle term. Consequently, I don't have a perfect square trinomial. Let's try another strategy. I think I'm going to go ahead and try some trial and error. I have x to the 4th plus 15x squared plus 64. I need to think of two numbers that multiply to 16 and add to 15, specifically two integers that multiply to 64 and add to 15. I don't know about you, but no pair of numbers is coming to me that has that property. But before I give up, I need to be very methodical in my search. So let's go ahead and be very methodical and look for a pair of integers that multiply to 64 and add to 15. Let's begin with 1. 1 times 64. Do those add to 15? Nope. Let's move on to 2. 2 times 32. Do those add to 15? Nope. We can go by 3 because it doesn't evenly divide into 64. How about 4? 4 and 16. Nope. Those don't add to 15. 5, 6, 7, none of those evenly divide into 64. How about 8? 8 and 8, those don't add to 15. They add to 16. Pretty close, but pretty close isn't good enough in factorization. The next integer that evenly divides into 64 is 16. I have a repeat pair. Once I have a repeat pair, I can give up the search. It must be the case that the trinomial x to the fourth plus 15x squared plus 64 is prime. Let's move on to difference of squares. Let's begin with our special product a plus b times a minus b equals a squared minus b squared. Those binomials on the left are called conjugates. They're similar expressions, the only difference being the operation between the two terms. The expression on the right is called a difference of squares. A squared's a perfect square, b squared's a perfect square. We're going to turn this into a factor formula by reordering it as a squared minus b squared equals a plus b times a minus b. A difference of squares factors into a product of conjugates. Let's see some examples. How about 25x to the fourth minus 9y squared? This is a binomial, so maybe it's a difference of squares. If a squared is going to be 25x to the fourth, a needs to be 5x squared. If b squared is going to be 9y squared, b needs to be 3y. So let's take our expression 25x to the fourth minus 9y squared, and let's rewrite it as 5x squared quantity squared minus 3y quantity squared. These two expressions are equal. 5 squared is 25, x squared squared is x to the fourth, 3 squared is 9, and y squared is y squared. I do indeed have a difference of squares. A difference of squares always factors into a product of conjugates. So I'm going to take the expression 5x squared plus 3y and multiply it by 5x squared minus 3y. As in all examples in this lesson, please do check by expanding out this factorization and seeing that it is 25x to the fourth minus 9y squared. How about 1 minus 400y to the 14th? Well, if a squared is going to be 1, clearly a needs to be 1. If b squared is going to be 400y to the 14th, to get the coefficient of 400, I guess the coefficient on b needs to be 20, and to get y to the 14th, the exponent on y in b needs to be 7. So I can take my given binomial, 1 minus 400y to the 14th, and I can rewrite it as 1 squared minus the quantity 20y to the 7th squared. This is definitely a difference of squares. A difference of squares always factors into a product of conjugates. I'm going to factor this into 1 plus 20y to the 7th times 1 minus 20y to the 7th. And something you're going to do is you're going to check and make sure that this factorization is correct. How about 25x squared plus 9? Well, one thing's for sure. This is not a difference of squares. And the reason I know that's for sure is because this isn't the difference of anything. This is the sum of two terms. Now, a lot of people, when they look at this, they think it factors. Well, let's think that through. If 25x squared plus 9 factors, we could consider the factorization by imagining there being a middle term, and the middle term would have to be 0x. So let's ask ourselves this question. What pair of integers could we find that multiplies to 25 times 9, which is 225, and adds to 0? Well, there's not going to be a pair of integers that has that property, because if the pair of integers multiplies to 225, the two integers have the same sign. And if you add two integers with the same sign, you're not going to get 0. You're either going to get plus plus plus, which is plus, or you're going to get minus plus minus, which is minus. Either way, you're not going to get 0. Nonetheless, I understand that sometimes, especially when you're taking a test, you get a little panicky. And so you might start panicking and thinking, why doesn't this factor into 5x plus 3 quantity squared? Well, if that happens to you, I have a little suggestion. Go ahead and rewrite 5x plus 3 quantity squared as the actual product of two factors of 5x plus 3. Then, when you multiply 5x plus 3 times 5x plus 3 using FOIL, I think what you'll see is that, the middle two terms don't add to 0x, they add to 30x. So it just is not the case that 5x plus 3 quantity squared is 25x squared plus 9. 25x squared plus 9 is prime. Any way you look at it. Let's look at w to the fourth minus t to the fourth. What do I square that gives me w to the fourth? That would be w squared. What do I square that gives me t to the fourth? That would be t squared. So I can take my expression w to the fourth minus t to the fourth, and I can rewrite it as w squared squared minus t squared squared. Difference of squares. Factors into a product of conjugates. W squared plus t squared times w squared minus t squared. This time I have two binomials, but one of those binomials factors. Which one? The one that's a difference of squares. W squared minus t squared is a difference of squares. So I can go ahead and factor that into the product of conjugates, specifically w plus t times w minus t. So this is the first time you've seen this, that sometimes after you perform your first factorization, the resultant trinomial or binomial factors further. And please do multiply out my proposed factorization and see that you do get w to the fourth minus t to the fourth. All right, let's move on to sum or difference of cubes. We have two special forms that address sum and difference of cubes. The first addresses the sum of cubes, a cubed plus b cubed. That's the sum of two perfect cubes. And that factors into a plus b times a squared minus ab plus b squared. Likewise, the difference of cubes, a cubed minus b cubed, factors into a minus b times a squared plus ab plus b squared. Now, these formulas are a little more complicated than the ones that we've seen earlier, so I do want to give you a little tip about how I keep these formulas straight in my head. Notice that the sign in the middle of the binomials on both sides of the equal sign are the same. A cubed plus b cubed, a plus b. A cubed minus b cubed, a minus b. Then I have a trinomial, and the one thing that I remember about the trinomial is that the sign in front of AB is the opposite sign that we had between our two terms in our binomial. So when we have a plus b, we have a minus sign in front of AB, and when we have a binomial of a minus b, we have a plus sign in front of AB. One more thing about this, a common error is that people will put a 2 in front of this AB term, so watch out for that error as well. Something that's kind of nice about these special form binomial sums and differences is that once you perform the first step of the factorization, the resultant trinomial never factors. And let's look at a specific example and kind of get a sense of why it never factors. Let's think about what we would get if a was x and b was 3, and we were using the form a squared plus ab plus b squared. The resultant trinomial would be x squared plus 3 times x plus 9. Does that factor? Are there a pair of integers that multiply to 9 and add to 3? Well, I don't think so. There's no way that we're going to get two integers that add to the weenie sum of 3 and multiply to the great big product of 9. Let's be very deliberate about it. What pairs of integers, positive, multiply to 9? 1 and 9, and 3 and 3. Neither of those add up to 3 in the middle. The residual trinomial, when you factor sum or difference of cubes, never factors. Now, we haven't ever seen this special product before, so before we actually do any examples, I do want to verify this special product. Let's go ahead and look at a plus b times a squared minus ab plus b squared. Distributing a through the trinomial, we get a cubed minus a squared b plus ab squared. Distributing b through the trinomial, we get plus a squared b minus ab squared plus b cubed. Do we have any common terms? You betcha. A squared times b with a minus sign in front of it, and a squared times b with a plus sign in front of it. Those two terms add to 0. Here we have plus ab squared. Here we have minus ab squared. Those terms also add to 0. What am I left with? A cubed plus b cubed. I've just verified my sum of cubes formula. Let's make one little observation here. What made all these things add to 0? Well, a big part of what made all these terms add to 0 is the fact that we had a plus sign here and a minus sign there. So that might help you remember that you have to have the different sign here than you had here. Let's factor 8x cubed minus 125. Is this a difference of cubes? Well, what can I cube that would give me 8x cubed? Since 8 is the cube of 2, I guess a would have to be 2x. What do I cube that gives me 125? Well, that 5 at the end makes me think 5, and 5 times 5 is 25, and 25 times 5 is 125. So b is 5. Let's go ahead and factor. We want to factor 8x cubed minus 125. The formula for factoring the difference of cubes is pretty complicated. So most people have the best chance of success if they just literally go ahead and write down the generic formula on their paper. And the generic formula here is a cubed minus b cubed equals a minus b times a squared plus ab plus b squared. So let's go ahead and take our binomial and rewrite it as 2x quantity cubed minus 5 cubed. And then looking at our pattern, let's go ahead and factor. This is going to be a minus b, that's 2x minus 5, times a squared, 2x quantity squared is 4x squared, plus a times b, 2x times 5 is 10x, plus b squared, that's plus 25. This one, you really could use the practice. Please do check. Expand out that proposed factorization and make sure that it really does equal 8x cubed minus 125. Let's do this supposed sum of cubes. Is there an expression I can cube that gives me 64? Well, let's think about it. 2's not going to work because 2 cubes just 8. How about 4? 4 times 4 is 16, and 16 times 4 is 64. So a is 4. Can I cube an expression and get 27t cubed? I sure can. That would be 3 times t. So I'm going to take my 64 plus 27t cubed, and I'm going to think of it as 4 cubed plus 3t quantity cubed. Let's go ahead and recall our factorization formula. A cubed plus b cubed equals a plus b times a squared minus ab plus b squared. So this sum of cubes is going to factor into a plus b, that's 4 plus 3t, times a squared, 4 squared is 16, minus a times b, 4 times 3t is 12t, plus b squared. 3t quantity squared is 3 squared, which is 9, times t squared. And again, please check this. Let's do one last example. Let's factor 8x cubed y to the 6th plus 64y cubed. This time, both terms in my binomial are perfect cubes. But I'm going to remember a lesson I learned in an earlier example. What's the first step in all factorization? It's to factor out common factors. So the first thing I want to do is look and see, do I have any common factors? And I'm seeing them all over the place. 8 evenly divides into 8, and it also evenly divides into 64. So I can factor out a common factor of 8. I'm also noticing that both of the terms have factors of y. As a matter of fact, they both have at least 3 factors of y. So I can factor out y cubed. When I do that, what do I leave behind? Well, for my first term, I leave behind 3 factors of x, and I also leave behind 3 factors of y. What do I leave behind from my second term? I think the only thing I'm leaving behind from my second term is 8. I am going to check and make sure I did this factorization correctly. 8y cubed times x cubed y cubed is 8x cubed y to the 6. 8y cubed times 8 is 64y cubed. Do I now have a sum of cubes? Is there an expression I can cube that gives me x cubed y cubed? Sure, xy. What can I cube that gives me 8? That would be 2. So my a is xy and my b is 2. I find it easiest to factor sums and differences of cubes if I'm actually looking at the formula. So the formula here is a cubed plus b cubed equals a plus b times a squared minus ab plus b squared. So my a plus b is going to be xy plus 2. My a squared minus ab plus b squared is going to be the quantity xy squared. When I distribute the exponent, I'm going to have x squared, y squared. Then I have minus ab. That's minus 2xy. And then I have plus b squared. That's plus 2 squared, which is 4. And once again, you really do need to go ahead and expand out this supposed factorization and see that it does indeed result in 8x cubed y to the 6 plus 64y cubed. And that ends my portion of the lesson, so now I'm going to turn it over to Anne.